Welcome to Spaceverse, your portal to cosmic adventures. Westerlund 1. It's not a name that rolls off the tongue like Andromeda or Orion, but in the world of astronomy, it's one of the most exciting places in our galaxy. Why? Because Westerlund 1 is a supermassive young stellar cluster, and not just anyone. It's the closest supermassive star cluster to Earth, located just 12,000 light-years away in the Milky Way. And now, astronomers have taken a deep dive into this cluster using the incredible power of the James Webb Space Telescope. With its ability to see through dust and into the hidden heart of star-forming regions, JWST is transforming our understanding of how stars, and even planets, form in the universe's most extreme environments. Westerlund 1 is no ordinary cluster. Spanning 6.6 light-years, this stellar megacity has a mass equivalent to around 63,000 suns. It's the kind of place where stars are born in abundance, especially the giant ones. Supermassive star clusters like Westerlund 1 are a breeding ground for stellar giants. They form where star-creating processes are highly efficient, thanks to thick clouds of gas and dust that collapse under gravity to birth stars. In clusters like this, the birth of stars and the planetary systems that often follow is accelerated to a cosmic frenzy. And this particular cluster? It holds the largest and most compact population of monster stars in the Milky Way. Hundreds of very massive stars, all packed into a relatively small region. It's the perfect storm of cosmic chaos, and astronomers have been eager to understand what's really going on in there. The new image and scientific findings from Westerlund 1 come to us courtesy of the extended Westerlund 1 and 2 Open Clusters Survey, or UOCS. This ambitious project brings together multiple observatories, JWST, Hubble, ALMA, Chandra X-ray, and more, all working together to decode the mysteries of massive stellar clusters. According to Mario Giuseppe Garcello, UOCS team leader from the Palermo Astronomical Observatory in Italy, we pushed our detection limit down to the brown dwarfs of the cluster, which are the smallest stars that can form. That's no small feat. Brown dwarfs are often considered failed stars, objects too small to sustain hydrogen fusion like our Sun, but too large to be called planets. Detecting these dim objects is incredibly difficult, especially in dense, chaotic clusters. But thanks to Webb, the UOCS team is now able to uncover the true contents of Westerlund 1, including the mass distribution of its stars, from the biggest giants to the smallest brown dwarfs. Why does that matter? Well, by measuring the full range of stellar masses, scientists can better understand how stars form under extreme conditions, something that has implications for everything from galaxy evolution to planet formation. And speaking of planets, JWST has something to say about that too. Because Webb observes in the infrared, it can detect young stars that are still wrapped in protoplanetary disks, the swirling rings of dust and gas from which planets are born. These may be forming planets right now, Garcello said. Just think about that. Amid the chaos of hundreds of massive stars exploding with radiation, fragile planetary systems may still be taking shape. How do they survive? How are they influenced by such violent surroundings? That's exactly what UOCS is trying to find out. All this, Garcello continued, will allow us, for the first time, to determine the impact of the starburst environment on the products of star formation and the process of planet formation. Starburst environments, where stars are born rapidly and in large numbers, are usually associated with galaxies colliding or undergoing major upheaval. These were common in the early universe, but they're much rarer today. That makes Westerlund 1 especially important. It's a rare glimpse into conditions that were typical billions of years ago. The Milky Way today hosts only a few supermassive clusters, with less than 10 known, Garcello explained. These few regions are crucially important because they allow us to study star and planet-forming conditions which are typical of starburst galaxies in the early universe, and to extend our knowledge of star and planet formation to the most extreme and energetic star-forming environments we know of. But these clusters don't give up their secrets easily. Superclusters like Westerlund 1 are often obscured by clouds of gas and dust and buried in dense star fields. Ordinary telescopes that see only visible light just can't peer through that mess. That's where JWST comes in with its huge light-gathering power and its ability to see in the infrared, which can penetrate those dusty clouds. To explore Westerlund 1, the UOX team used JWST's two main tools, the mid-infrared instrument, or MIRI, and the near-infrared camera, or NIRCam. These instruments are designed to cut through the clutter and reveal what's hiding beneath the dust. And what they found was surprising. The main surprises arrived from the MIRI images, Garcello said. Those images showed a dense and structured nebulosity, clouds of gas and dust, not just around Westerlund 1, but within the cluster itself. Now, here's the weird part. Westerlund 1 is about 5 million years old. Normally, clusters with massive stars clear out their birth clouds within about 1 million years. The powerful radiation and stellar winds from these giant stars sweep the region clean in relatively short order. But Westerlund 1 still has nebulosity. Why? Garcello explained, "We think we are witnessing the accumulation of intercluster material from the gas and dust ejected by the most massive stars of the cluster during their final stages of evolution. In other words, these clouds aren't leftovers from star birth. They're new, made from material blown off by dying stars. The cluster is essentially polluting itself, recycling its own stellar material." The MIRI images also revealed peculiar outflows and shells around the most evolved massive stars in Westerlund 1. These structures may offer insight into how these stars are losing mass as they prepare to go supernova. And there's more to come. Over the next 2 to 3 years, the UOX team plans to publish a wide range of findings from this project. Next up, a study of the hot intracluster gas using diffuse X-ray emissions. Then they'll analyze high-energy phenomena around compact objects in the cluster, possibly neutron stars or black holes. They'll also measure the mass distribution of low-mass stars, study the disk-bearing population, and investigate the outflows surrounding red supergiants and yellow hypergiants. And remember, this isn't just about JWST. UOX is using data from other world-class observatories too, like Chandra for X-rays, ALMA for millimeter waves, and Hubble for optical and ultraviolet light. But JWST is the linchpin. It's giving scientists the first true look into the darkest, dustiest, most chaotic regions of our galaxy, where stars are born in bulk, where giant suns explode, and where, maybe just maybe, planets are forming in the shadows of cosmic titans. As Garcello concluded, besides these, the analysis of the observations of Westerlund 2, a slightly less massive but younger cluster than Westerlund 1, is at a good stage, and we will start publishing those results soon. So stay tuned. We are just beginning to uncover the hidden drama playing out inside Westerlund 1, and thanks to JWST, we now have front-row seats to one of the most spectacular shows in the galaxy. And that's it. Thanks for exploring the heart of Westerlund 1 with us, a cosmic powerhouse where stars are born, planets may be forming, and the universe reveals its wildest secrets. With JWST leading the way, there's so much more to uncover. Until next time, keep your eyes on the stars.